Let us learn about some of the widely present geogenic groundwater contaminants, their health impacts and geographical spread. Fluoride is one of them. Fluorine is the lightest member of the halogen group of elements and most electronegative of all elements. The concentration of fluoride in the continent crust is 625 mg per kilogram. Various rock types contain fluoride at different levels. For example, basalt 360 microgram per gram, granite 180 microgram per gram, limestone 220 microgram per gram, sandstone 180 microgram per gram, shells 800 microgram, ocean sediment 730 microgram per gram, and soils 285 microgram per gram. There are several geographical belts across the world having rocks and soils with high fluoride content, and India lies in one such belt. Besides, out of 85 million tons of fluoride deposits on the earth crust, about 12 million tons are found in India. Fluorite is a common fluoride mineral but has low solubility and occurs in sedimentary and igneous rocks. Apatite commonly contains fluorine. There are many minerals which contain fluorine. Besides mineral, it is commonly present in plants, soil, phosphatic fertilizers and rock minerals. There are several potential solubility controls that limits dissolved fluoride concentration in water. It appears that high fluoride concentration is more likely to occur in water that has a low concentration of calcium. In solution, it forms fluoride and forms strong solute complex with many cations. Fluoride occurs as a natural secondary constituent and varies between 0.01 to 10 mg per liter in groundwater. The Bureau of Indian Standards recommended 1 mg per liter as the acceptable limit of fluoride in drinking water. However, in the absence of alternate source, the permissible limit is 1.5 mg per liter. The WHO's prescribed guideline value for fluoride is 1.5 mg per liter, and a presence in excess make it one of the major geogenic contaminants. American and European dentists have started linking dental staining and fluoridation by the start of 20th century. However, the first case of fluorosis in India was reported in the year 1937 from Guntur district of Andhra Pradesh. By 1950, endemic fluorosis was also reported from Punjab, Tamil Nadu and Uttar Pradesh. In the last few decades, numerous studies were carried out to measure the concentration and to map the geographical extent of endemic regions and delineate the factors regulating fluoride contamination. At present, 201 districts of 20 Indian states are reported to be affected by fluoride in groundwater. Fluoride is widely prevalent in different parts of India, particularly in Andhra Pradesh, Tamil Nadu, Uttar Pradesh, Gujarat, Rajasthan and Telangana. Concentration of fluoride in drinking water is different parts of country vary from 0.5 to 50 mg per liter. The fluoride content much higher than the permitted maximum limit have been found in many areas throughout the world such as US, Italy, Netherlands, Spain, France, Germany and Switzerland. The problem is severe in India and other such developing countries because a major proportion of the rural population is dependent on the available surface water or groundwater sources for their day-to-day requirements. The principal source of fluoride to physiology of a man are water and food. About 96% of fluoride in the body is found in bones and teeth. Fluoride is essential for formation of dental enamel and normal mineralization of bones. Calcium-rich constituents of teeth like enamel and dentine have a strong fluoride affinity during teeth formation. Fluoride in small doses has a remarkable influence on dental system by inhibiting dental caries. However, fluoride content of more than 1.5 mg per liter in drinking water leads to 4 types of fluorosis. It is known as dental fluorosis, skeletal fluorosis, gut fluorosis and combination of all of these situations. The long exposure and use of groundwater having high fluoride content result in dental fluorosis. At still higher concentration, skeletal fluorosis occur. The disease affects the bone and ligaments. Intake of 20 to 40 mg fluoride per day over a long period of time result in crippling skeletal fluorosis. The degree of manifestation of fluorosis has been related to fluoride concentration in drinking water and the period of consumption. The problem of endemic fluorosis occur with varying intensity in different parts of the country. The skeletal and dental health of about over 60 million people is at this risk due to high fluoride exposure levels. Hence, fluoride is often called a two-edged sword. The most important aspect of prevention and control of endemic fluorosis is to generate a database on the endemic presence of fluoride across the country and create awareness among the population about health issues related to consumption of groundwater enriched with fluoride. Several methods have been advocated for defluoridation of drinking water. These methods can be broadly divided into two categories. First one, those based on the addition of some material to water during softening or coagulation process, and second one is methods based on iron exchange or adsorption process. Nalgonda district of Telangana is one of the most severely affected regions in the country. More than 3 lakh people in the district are affected with skeletal and dental fluorosis, a stigma that has struck for generations. However, with the implementation of Mission Bhagiratha, a flagship scheme of Government of Telangana to supply surface water for drinking and daily use purposes, no new case of fluorosis reported in Nalgonda district in last 6 years. It shows that investment for providing improvised drinking water with the challenge of fluorosis can be tackled. Similar to fluoride contamination, arsenic contamination is another widespread and endemic groundwater contamination problem faced by sizable population of the country. Arsenic is 20th most abundant naturally occurring element, which occurs pervasively in all spheres of the planet. The concentration of arsenic in the continent crust is 1.8 mg per kilogram. Its mean concentration in igneous rock is 1.5 to 3 mg per kilogram, where in sedimentary rocks it ranges from 1.7 to 400 mg per kilogram. Arsenic, which is abundant in Earth's crust, also found in other natural environments in small quantities. Transport and distribution of arsenic in the environment are complex, and there is a continuous cycling of different forms of arsenic through air, soil, and water. Arsenic is generally concentrated in magnetic sulfide and iron ores. It may also come from anthropogenic sources. The most common oxidation state of arsenic is arsenide and arsenate. Arsenic can exist both in organic and inorganic forms. However, inorganic forms are more toxic than the organic ones. Dissolution of minerals and ores and erosion from natural resources introduced arsenic in soil and groundwater. Among various natural pools, the greatest concentration of arsenic occur in groundwater due to extended water-rock interaction. It happens as the aquifer environment is conducive to accumulation and mobilization of arsenic. Inorganic arsenic is commonly present in groundwater as arsenate and arsenite. With the change in oxygen availability in the surrounding environment, these states may interchange by oxidation and reduction reactions. Hence, the concentration of arsenic in natural waters, which depends on the geological composition, may vary widely depending on redox condition in the geological environment. Based on the arsenic geochemistry, 3 probable mechanisms of arsenic mobilization in the groundwater has been proposed. The initial case of extensive arsenosis had been reported from Argentina in 1939, followed by Taiwan in 1968. However, after discovering the occurrence of arsenosis in Bengal Basin of eastern India and Bangladesh, it became a topic of extensive global research. Over the past 5 decades, gradually elevated arsenic concentration in groundwater above the WHO guidelines values of 10 microgram per liter has been detected in more than 40 geological provinces, endangering more than 200 million people worldwide. Currently, the world's 5 most prominent areas facing a wide groundwater arsenic contamination and the worst suffering of the people are from Asia. It includes Bangladesh, West Bengal of India, Inner Mongolia and Xinjiang province of China, and Taiwan. In all these regions, extensive groundwater withdrawal is taking place because of agricultural irrigation. Most arsenic affected areas are located in Southeast Asia, Bangladesh and West Bengal, risking the health of 150 million people. 47 districts in Bangladesh and 9 districts in West Bengal have arsenic level in groundwater above the maximum permissible limit of 50 microgram per liter. In addition to West Bengal, presence of naturally elevated arsenic level in groundwater has also been reported from Chhattisgarh, Bihar, Jharkhand and Uttar Pradesh. However, the extent of problem in these states is not fully known. Recently, investigation reported arsenic contamination in groundwater of northeastern states like Assam, Tripura, Manipur, Arunachal Pradesh and Nagaland. Arsenic was detected in 20 districts of Assam out of 23 and 3 districts of Tripura, 1 district of each of Manipur, Arunachal Pradesh and Nagaland. Ingestion of inorganic arsenic can result in both cancer and non-cancer health effects. Arsenic interferes with a number of essential physiological activities, including action of enzymes, essential cations, and transcriptional events in cells. Chronic exposure to low arsenic level has been linked to health complications, including cancer of the skin, kidney, lung, and bladder, as well as other diseases of skin, neurological, and cardiovascular system. The US Environmental Protection Agency has classified arsenic as a Class A human carcinogenic and in 2001 adopted a new standard for arsenic in drinking water at 10 microgram per liter, replacing the old standard of 50 microgram per liter. This alarming picture of the arsenic contamination in groundwater in the region and continuous consumption of arsenic enriched groundwater can pose serious health hazard to local population. Therefore, a thorough survey is needed to assess the magnitude of problem in these states and take appropriate measures like generating awareness about health problems associated with the arsenic and providing safe drinking water to affected population. Now let's talk about another geogenic contaminant, which is uranium. Uranium or U is a ubiquitous trace element of the Earth's crust with an average concentration of 2.6 to 2.8 mg per kilogram. It is the heaviest natural occurring member of the periodic table. Though considered to be rare, it is more plentiful in nature than several other trace elements and rare earth elements. It has been classified as a lithophilic element and occurs naturally in varying degree in all minerals, rocks, soils and water. It has 3 naturally occurring radioisotopes with very low specific activity, thereby making its radiologically toxicity a less significant concern compared to its chemical toxicity. Non-toxic level of uranium is found in almost all natural water bodies, and exposure from drinking water is usually very mild. However, at elevated levels, drinking water can become a chief source of non-professional uranium exposure. Concentration in groundwater are usually less than 1 microgram per liter. However, it is susceptible to natural uranium accumulation due to extended water-rock interaction with elevated concentrations. Though most studies over the past decades have focused on uranium mobilization from anthropogenic sources, many recent studies from around the globe have now recognized uranium concentration above 30 microgram per liter in the groundwater resources occurring from natural sources. Though uranium content of rock typically range from 1 to 4 microgram per kilogram, relatively high uranium concentrations have been recognized in granitic and other late phase magmatic, argillaceous and organic rich deposits, ferruginous and phosphatic sediments and metamorphic rocks derived from them. Therefore, uranium-enriched groundwater is expected to occur in two broad hydrogeological settings: granitoid basement aquifers and certain sedimentary basins. High uranium groundwater have been reported from many crystalline aquifers worldwide, including Precambrian granitic basement of India. The localized occurrence of uranium in groundwater has been reported from Andhra Pradesh, Telangana, Chhattisgarh, Gujarat, Haryana, Himachal Pradesh, Jharkhand, Karnataka, Maharashtra, Odisha, Punjab, Rajasthan, Tamil Nadu, Uttar Pradesh, West Bengal and Jammu Kashmir. As per Bureau of Indian Standards, the maximum permissible limit of uranium is 30 microgram per liter in all drinking water standards after following due process. An increased in concentration may be having dire health consequences on the exposed population. Toxic effects of uranium exposure have often been linked to nephritis, change in the bone structure and different type of cancers. Now let's talk about another geogenic contaminant which is very common in occurrence across the earth crust. Iron is the second most abundant metallic element in the Earth's outer crust. However, it is present in minor concentration in water. Iron content is relatively high in few igneous rock minerals. Availability of iron in an aqueous solution is strikingly affected by environmental conditions, especially change in degree or intensity of oxidation and reduction. The extent to which Fe dissolve in groundwater depend on the amount of oxygen in the water and to a lesser extent upon its degree of acidity. When level of dissolved oxygen in groundwater are greater than 1 to 2 mg per liter, iron occurs in a ferric state, while at lower dissolved oxygen levels, the iron occurs as a ferrous state. Although ferrous is soluble, ferric is insoluble in normal pH level. In the groundwater, the dissolved oxygen is less, iron will dissolve rapidly, particularly if the pH of the water is acidic. Dissolved oxygen content is typically low in deep aquifers and also in the aquifer containing organic matter. Decomposition of the organic matter depletes the oxygen in the water and the iron dissolves as a ferrous. When this water is pumped to the surface, the dissolved iron reacts with the oxygen in the atmosphere, changes to oxidized or ferric and forms rust-colored iron minerals. High iron makes the water taste astringent. The water may appear brownish due to precipitation of ferric hydroxide and may form red oxyhydroxide precipitates that sustain laundry and plumbing fixtures, and therefore it is an objectionable impurity in domestic and industrial water supplies. According to the US EPA, although iron in drinking water is safe to ingest, the iron sediments may contain trace impurities or harbor bacteria that can be harmful. Iron is an essential element in the metabolism of animals and plants. The most well-known role that iron plays in human nutrition is the formation of protein, hemoglobin, which transport oxygen to all cells of the body. Chronically consuming excess amount of iron can lead to a condition known as iron overload. This condition is usually the result of gene mutation. If left untreated, iron overload can lead to hemochromatosis, a severe disease that can damage the body's organ. Elevated level of groundwater iron have been reported by the Central Groundwater Board from several aquifers of the country. The high concentration of iron in groundwater has been observed in more than 1.1 lakh habitations in the country. Groundwater contaminated by iron has been reported from Assam, West Bengal, Odisha, Chhattisgarh and Karnataka. Localized pockets are observed in states of Bihar, Uttar Pradesh, Punjab, Rajasthan, Maharashtra, Madhya Pradesh, Jharkhand, Tamil Nadu, Kerala and northeastern states.